Today we're going through magnetic fields for A-level physics. So let's get started with the magnetic field on a magnet. So a magnetic field is a region where forces are exerted on magnetic materials. And it can be represented using field lines, also called flux lines, where the closer the lines, the stronger the field. Now let's show these field lines on magnets. So a magnet looks something like this, where you have a north side and a south side. So the field lines around this magnet will look something like this. So yes, these field lines do have a direction from the north to the south. They always go from north side to the south side. And let's draw two other examples of magnets. So say you have a magnet that looks something like this, where you have two north poles. The field lines will look something like this. So they'll go away from the north. And this region in the center, the fields cancel out, so you have no lines. And this can be the same for south. Instead of north poles, you have south poles, except the field lines will go towards the magnets instead. So let's do one more example. And you've got a north pole here and a south pole here. And the field lines will just go away from the north and towards the south. So now let's move on to the magnetic field on a wire. There's always a magnetic field around the wire that carries an electric current. So say if you have a wire like this, with a current going this way, you have a magnetic field induced going something like this. And the field lines are concentric circles centered on the wire. And to memorize this, you can use the right hand rule, where you have your thumb pointing upwards, and the rest of your fingers will curl like this. So this will be your thumb, and these will be the rest of your fingers. And this is called the right hand rule. But if you form a loop with a wire into a coil, the fields create a donut shape. But a coil with a length forms a solenoid. So say you have a loop of wire like this, your fields will look something like this in a donut shape. And if you have a coil that has a length, this will make a solenoid, and it will form a field similar to a bar magnet. So say you have a solenoid which looks like this. The field will look similar to that of a bar magnet. Now let's move on to force on a wire in a magnetic field. So if a wire carries a current in a magnetic field, it will experience a force. This is because the wire has a magnetic field of itself, and if it's in another magnetic field, it will cause a resultant field. And where the lines are closer, there will be a stronger field, so a stronger force on the wire, so we'll experience a force, a net force in one direction. So let's draw it out. So if we have a magnet that looks something like this, and say you have a current carrying wire in the middle, like this, and the current is going away from the page, away from the screen, you'll have a field lines that look something like this, where these are the magnetic field lines of the magnets, and these are the magnetic field lines of the wire. Now let's draw a resultant field. If that's your wire, your field lines will look something like this. And this will cause a force on the wire in this direction, F. The direction of this force is always perpendicular to the current of the wire and the magnetic field which the wire is in. So if the current is parallel to the field lines, so you have the wire going this way, for example, you would have a zero force. So because it has to be perpendicular of each other, as you can see, the wire would be coming outside of the page, and this one would be going to the right. The field lines will be going to the right. And you can find the directions of the force using the current and the magnetic field using Fleming's left-hand rule, where you use your left hand and use three fingers, your thumb, your index finger, and your middle finger, each finger going into every 3D direction. And you can use the acronym FBI, where F is the force, B is the direction of the magnetic field, and I is the direction of the current, conventional current. It's worth noting that the force is dependent and is proportional to the current, and it's also proportional to the magnetic flux density of the magnetic field. where the magnetic flux density is force on a meter of wire carrying 1 ampere of current at right angles to the magnetic field, which can be described using an equation where this only works when the current is at 90 degrees to the magnetic field, and the equation is F is equal to BIL, where F is the force, B is the magnetic flux density, I is the current, and L is the length of wire within the magnetic field. So now let's move on to the force of a charged particle in a magnetic field. Just how like a wire that carries current through a magnetic field feels a force, a charged particle in a magnetic field that moves also feels a force. So there's a formula that describes the force that acts on a charged particle in a magnetic field depending on its velocity. So using the F is equal to BIL formula, so from before, we can rearrange the I to be equal to Q over T, and the length is equal to the velocity times time. And if you substitute these two into the equation, you're going to get F is equal to B Q over T times V times T. And you can realize that this is over T and this is T, so these two can cancel out. And you'll get F is equal to B Q V. Because distance is equal to velocity times time and current is equal to charge over time, you'll get force is equal to the magnetic flux density times the charge of the particle times the velocity that the particle is moving at. So now let's move on to the path of charged particles in a magnetic field. So charged particles in a magnetic field are deflected in a circular path. So using Fleming's left-hand rule, we can see that the force is perpendicular to the magnetic field and is perpendicular to the current. So because the direction of current can be replaced with the direction of the velocity of the particle, we can see that the force is perpendicular to the direction of travel. Therefore, the particle would travel in circular motion because the force is perpendicular to the direction of travel, as this is the condition for circular motion. Now, because F is equal to BQV, we can see that the force is independent of mass of the particle. However, if we equate this to the force of circular motion, because this is the force providing circular motion, we can make mv squared over r, which is the equation for the force in circular motion. If we equate these two, because it's the same force, because the force of the magnetic field is the one holding the particle in circular motion, so we're going to get mv squared over r is equal to bqv. If we rearrange this equation, we can find the radius of the circular path, because if you rearrange and multiply by r on both sides, you're going to get r here. If you divide by v, the square's going to cancel out. Divide by b and q, they're going to be left at the bottom, so you're going to get r, which is on this side, is equal to m times just 1v, get rid of the squared, over bq, which is left at the bottom here. So we got this by equating both forces because they are the same. So from this equation, we can see that the larger the mass and the larger the velocity of the particle, the larger the radius of the circular path. But if the magnetic field is stronger, so a larger magnetic flux density and a larger charge of the particle, you're going to get a smaller radius because at the bottom is divided by. So a convention, so let's draw out how it looks. So if we were to draw a magnetic field, for it to come away from the page, we can say the field looks something like this. And if it goes towards the page, it will look something like this. So this is for any field lines. So say we have a magnetic field which looks something like this, where the magnetic field is going towards the page, or the magnetic field is going into the page. If we have a positive charged particle, it would look something like this. So say we have a positive charge and it's moving in this direction over here. If we use Fleming's left-hand rule, we can see that the particle would deflect in a circular path like this. Why? Because it feels a force in this direction. Now say we have a magnetic field going away from the page like this, and now you have a negative particle instead, which follows a path like this. Which way would it deflect? So using Fleming's left-hand rule, we would make our velocity negative because this is conventional current. So if it's a negative particle, negative charged particle, we would make our velocity go negative like this. So wherever your middle finger points, your velocity would be the opposite direction. So because the force is away from the page, you will have a curve that looks something like this, because the particle would feel a force in this direction. So these are two scenarios of how to apply Fleming's left-hand rule to find the circular path, or how the circular path looks like of charged particles in a magnetic field. So now let's move on to the cyclotron. Cyclotrons use circular deflection, where a cyclotron is basically a particle accelerator used in radiotherapy. And it's made of two semicircular electrodes like this, with a uniform magnetic field perpendicular to the plane of the electrodes. And an alternating potential difference is applied to the electrodes. So at the center, there's a source of charged particles, so like a radioactive source, for example, and the particles follow a circular path with increasing radius at the electrodes. So there's an alternating PD between the electrons. At the center, there's a source of charged particles, and the particle follows a semicircular path of increasing radius in the electrodes. This is because the potential difference between the electrodes accelerates the charged particles. So they get accelerated around here, 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 and here. And if they have a faster velocity, they're going to have a larger radius. So they're going to have an increasing radius as they go across the potential difference. And this is all in a vacuum. The alternating current needs to happen because if the charged particle is attracted to positive and repelled by negative, so this one will be negative, and this one will be positive, then the positive charged particle would be accelerated this direction. But now, once it's in the semicircular path in this direction, when it goes to this part here, it's going to be repelled by the negative and attracted to the positive. So it's not going to be accelerated, so it's going to be decelerated. So this is why you alternate the PD. So now that the positive becomes negative and the negative becomes positive, so they switch basically. Because now the charged particle is going to be repelled by the negative side and attracted by the positive side, and it's going to accelerate to the positive side. And they keep switching to accelerate more and more and more until it has a really high speed, because it accelerates a lot, and a large radius. So then it goes out and it accelerates the particles because it's a particle accelerator. So now let's move on to magnetic flux. Magnetic flux is like the number of field lines there are. And magnetic flux density, it measures the strength, like the field lines, per unit area. So the total magnetic flux passing through an area perpendicular to the magnetic field with a flux density B is defined as, so say you have an area like this, and you have magnetic field lines going this way, like this. If you have them at right angles to the area, so the flux, which is written as phi, is equal to the magnetic flux density B multiplied by the area. So this is when the area is at a right angle to the magnetic field lines. This is the magnetic flux density, and the area, which is in meters squared. So now let's move on to electromagnetic induction. So when a conductor cuts a magnetic field, so say you have a magnetic field that looks something like this, and you have a conductor that cuts through it like this, electromotive forces are induced in the conductor. So if you have relative motion between a conducting rod and the magnetic fields, electrons in the rod or in the conducting material will experience a force causing them to accumulate at one end of the rod. And this causes an EMF. And these are all the steps of electromagnetic induction. Now let's use Fleming's left-hand rule to find out how this works. So remember, we had the thumb as the force, the index finger as the magnetic field, and the current as the middle finger. So if we draw our rod and see how this electromotive force is induced, we see that if we're moving in a field, a magnetic field that goes this way here, for example, and we have a motion this direction, if we make our motion now the current, because we have charged particles inside the wire and they're moving this way, it's the same as the current. So we will replace the current as the motion in our left-hand rule, and our B stays the same. And if we look at the left-hand rule, we would have an electromotive force this way. So because this applies to positively charged particles, we would have an accumulation of positively charged particles on this side of the rod, and then leaving the negatively charged particles on this side. So the electrons will feel forced this way because remember this rule applies the opposite way using a negative charge. So the positive holes, you could say, in the rod will accumulate on this side, and the negative on this side. So you would have a potential difference or an EMF induced. So you can also induce an EMF in a flat coil or a solenoid by moving the coil or a magnet through the coil or a coil around a magnet. So in both of these cases, either you move a coil around the magnet or a magnet around the coil. In both cases, an EMF will be induced. This is because you have a change of magnetic flux. Because the further away the coil is to the magnet, the less flux it will have, and the closer it is, the more flux it would have. This is going to link later to an equation where we can find the EMF. And if you connect it to a circuit, a current will flow through the circuit, an induced current will flow through the circuit. So the type of current produced depends on the motion of the magnet. So for example, if you have a coil that looks something like this, if you move the magnet one way, you're going to get a potential difference that like this. So a current that goes minus and positive here. You move the magnet the other way, you're going to get it flipped. So you're going to get your positive here and your negative here, for example. So now let's move on to the equations for electromagnetic induction. So it's worth noting, the more turns in a coil you have, the larger the EMF is induced. So there's a property called flux linkage, which is the number of coils multiplied by their magnetic flux. We can use the rate of change of this quantity to tell us how strong the EMF will be in volts. And the flux linkage has a unit called Weber turns, and that's the unit of flux linkage. And it can be also calculated using an equation, so where you have your flux linkage, which we can write as N, which is the number of coils, times the magnetic flux, like this. And this altogether would be your flux linkage, and this will be equal to the magnetic flux density times the area of the coil times the number of coils. And as you can see, this will be very useful to find the flux linkage together. As you can see, the N is on both sides, and this equation just comes from the one we found before, which was phi is equal to BA. So a change in flux linkage of 1 Weber turn in 1 second will induce 1 volt in the loop of wire. And this can be represented using this equation where E is the EMF is equal to the N number of turns of a wire times the change in flux over change in time. So all of these equations so far are for when the magnetic flux is perpendicular to the area of the wire, because we said before in this equation that it has to be perpendicular to an area to find the flux using the magnetic field and an area. To use these equations when the magnetic flux is not perpendicular to the area of the wire, we will use trigonometry. So for example, the equation from before, which was phi is equal to BA, if we have a coil like this, so I'm going to draw in 2D with an area A, you can't really see it because it is facing this direction, so the area is 2D. And we have our field going this way. And now if your coil makes an angle to the field lines of theta, to use this equation now, you'll just multiply the BA times cos theta. And now remember the flux linkage equation, N phi is equal to BAN. For this equation as well, you'll multiply it by cos theta if you're working with angles that are not perpendicular to the field line, so coils that are not perpendicular to the field lines. And just remember, this is a coil, but this is a side view. So this is because we're using trigonometry for these equations because it is not perpendicular, so the area is not perpendicular to the field lines. So now let's move on to induction laws. The first induction law is called Faraday's law, and it says that the induced EMF is directly proportional to the rate of change of flux linkage. So it's basically this formula that we said before. So this is Faraday's law. And if we were to draw it out in a graph, we would get something like this. So say you have flux linkage against time, and you have a graph that looks something like this. So you're increasing your flux linkage over time. Your gradient would be the EMF. And if you have a graph of your EMF over time, the area under the graph would be your flux linkage. Another induction law is called Lenz's law, and this states that the induced EMF is always in a direction that opposes the change that caused it. So it's basically this equation, but you apply a negative because so you show the direction of the induced EMF. So this negative sign shows the direction of the induced EMF. And this law is so that it agrees with the conservation of energy. Because if you use energy to move a conductor through a field, a resistance will be caused by the magnetic attraction which produces the induced current. So you apply energy to move a conductor, which is used to induce an EMF, which causes a magnetic attraction, which is a resistance to the motion you used to move the conductor. So you have to do work to induce an EMF, basically. Again, like most laws, Lenz's law works when the conductor is traveling at right angles to the magnetic field. So if we look at Lenz's law using the Fleming's left-hand rule, we can see how this resistance of motion is applied, where this resistance of motion comes from. So to simplify Lenz's law, the EMF should produce a force which opposes the motion of the conductor, causing a resistance. Or it could also oppose the motion of the magnet, whichever one is moving, because the motion is relative. Because remember, either one of these can move and the EMF will still be induced. So first let's draw a diagram before we go on to Fleming's left-hand rule. We say we have a magnetic field that looks something like this, and you have a conductor like this. If you have a motion like this, you should also have a resistance which goes this way. Yeah, so if you have a motion which is perpendicular to the magnetic field and the direction of the induced current, then there should be a resistance force going upwards like this. Say the magnetic field goes this way. So say the current goes this way. So now let's look at this from Fleming's left-hand rule. So first, say we move the conductor. So we would have, so let's remember F, B, I. So remember, if we move the conductor, we're going to substitute that as our I. So if we move our conductor, our induced EMF will be the force. So we can substitute the force as EMF. So now we've moved the conductor this way and we've induced an EMF this way, and the magnetic field still goes this way. Now let's look at this scenario now. But now, because we've already moved the conductor, there will be an EMF running through the conductor. So there will be a current going through the conductor. So now I've made a new left-hand rule where we have flipped this sideways, so this way. So we're going to keep our B going towards the screen. So it's not the same, obviously, but it's going towards the screen, and these two would, let's just say this is along this axis of the screen, and then this one of this axis of the screen. So now we know our EMF is being induced this way, and because of FBI, so let's draw FBI again, because we flipped it, our new I would be then EMF, because the EMF would cause a current or a motion of the electrons or throughout the rod, which will cause a current through the rod. So we flipped it sideways this way, so the new I would be going up this way, the B stays the same. So now there'll be a force in this direction. Now if we compare these two, we can see that the motion goes in this direction, but the force goes in this direction. So if we draw this out, you would have the motion and you have the force. So because of the left-hand rule and Lenz's law, we can see that if you cause a motion of a conductor through a magnetic field, you would cause it to have an EMF induced, which will cause another force as a resistance because of two consecutive Fleming's left-hand rules. And this works if there is or isn't a circuit either. So now let's move on to alternators. And so what is the alternator? The alternator is a generator of alternating current. Now let's draw a diagram of how it looks. So here we have two magnets, a north pole and a south pole, facing each other to create a uniform magnetic field. And we have a wire in between, and these are called slip rings, and they're connected to an external circuit. So let's label the diagram. So yeah, you've got the magnets creating the uniform field in between, the wire, which is like this, and connected to the slip rings, which are then connected to an external circuit. So this is a type of generator, and generators and dynamos, where a dynamo is basically a DC version of this, convert kinetic energy into electrical energy. They do this by inducing an electric current by rotating a coil inside a magnetic field. So for example, in this case, in our generator or our alternator, we have a rotating coil, so it would go this way around, and this rotating coil will cause a change of magnetic flux. So this rotating coil inside of the magnetic field would cause a current to flow through it because there's a change in magnetic flux linkage. And as we said before, this creates alternating current. This is because the output voltage and the induced current change direction every half rotation. So every half a rotation, it will go one way, and every other half, it will go the opposite way. So the current would go one way and the other way. So sometimes the voltage will go this way around, and other times, so this way around is a circuit, and other times it will go this way around every half turn. And because this is connected to a circuit, it would be the same for the currents. So flux linkage and induced voltage are actually at 90 degrees out of phase. So when you have a coil rotating at an angular speed of omega, and when your angle is equal to omega t, because of your omega being your change in angle over change in time, if you rearrange, you're going to get this. So now if we put this value into the equation that we said before of when you're using induction laws for angles, you would have, so we'll use this equation, and instead of theta we'll substitute omega t. So if we write the new equation out, we're going to get n phi, which is the flux linkage, multiply BAN times cos omega t. And this equation relates the flux linkage to the magnetic flux density of the magnets in between. So for example, here, and the area of the coil of the alternator and the number of turns it has. And so in this case, it would only have one turn because it goes this way. And this relates to the flux linkage over time. And because we said before that if we have a graph of N, so our flux density over time, the EMF. So now we can make a new equation where we find the gradient of the previous equation we just did in terms of time. So if we were to draw a graph of flux density against time, if we find the gradient of this graph, we're going to get the EMF as we saw in the graph before. So our EMF would be equal to BAN times omega sine omega t, which is basically a differentiation if you do A-level maths. And this is because epsilon is equal to the change in flux linkage over the change in time. I normally use delta, but I'm using d in this case because it's a derivative. You don't really need to know this. You don't really need to know derivatives for A-level physics. So now let's draw a graph of how this would look like. So if we do two graphs, one of the flux linkage and one of the EMF. So here we have two graphs, one of flux linkage in Weber turns and one of EMF against time, both of them. And I've drawn them right next to each other to compare at the same time intervals what would happen. So if we look at the equations again, we're going to see one relates to cos of a multiple of time and one relates to the sine of a multiple of time. So for the Weber turns, we can just draw, so for the flux linkage, we can just draw a cos wave because it's related to cos. And because our time axis is arbitrary, it doesn't really matter at this point. We just need to know that it's related to cos. So this would be the flux linkage over time of an alternator. So now let's look at the EMF, and because this is related to sine, and it's a positive sine, we're going to just draw a sine wave. Also remember, because of Lenz's law, this is going to be in the opposite direction, so it's going to be a negative sign here. So that's why when you differentiate, if you know maths, if you know A-level maths, you're going to go from cos to negative sign, but because it's a negative, you're going to get multiplied by another negative, so you're going to get a positive value here. So we're going to just draw a positive sine wave, which looks something like this. So now, because we said it's the gradient of the line, so let's compare. So at the first point here, we see that this is a maximum gradient. And if we compare to the bottom side, we know that this is a 0. And because the gradient is 0 here, it's basically flat, we have a 0 EMF here. And if we look at this point here, here we have a negative gradient. So because we have the EMF going the opposite direction, we're going to have a positive EMF, really high EMF here. And here we have a gradient that isn't changing because it's basically flat. And here it also relates to a 0 EMF. And if we go here, you have an increasing gradient. That means you would have the negative of an EMF, so you'd have the minimum possible EMF. And again, here you have a flat gradient, so you'd have a 0 EMF as well. So these are the two graphs of the change in flux linkage over time and the change in EMF over time. Just remember that it's the negative of the gradient because of Lenz's law. So what does this relate to the real alternator, as we say here? We know that the EMF is 0 when the coil is perpendicular to the magnet, because there's most flux linkage, because you see when the most flux linkage there is, it relates to 0 EMF. And the EMF is the greatest when the coil is parallel to the magnetic field, because there's the least flux linkage. So this is when the EMF is 0 at 90 degrees, when the coil is at 90 degrees to the field, and the EMF is at its greatest when it's parallel to the field, when the coil is parallel to the field. So when the coil is at 90 degrees to the magnetic field, you have the most flux linkage, so you have a 0 EMF because of the graphs, and because when the coil is parallel to the magnetic field, you have the least flux linkage, so you have the largest EMF. So if we draw how this looks like, say we have the field going this way, and the coil looks something like this. So when the area of this coil is at 90 degrees, remember you have the most flux linkage. And when you have your coil 90 degrees to the field like this, so we'll see it from the side and it will look flat like this, and say the field is going through it. In this case, you have no flux linkage, so your EMF would be the largest because of the graph. So here you have your largest flux linkage, so therefore your smallest EMF. And here you would have your smallest flux linkage, so therefore you would have your largest EMF. And this is because the alternator is constantly rotating and it causes these two equations. So because it is rotating at a constant rate, or is constantly rotating, because it's constantly rotating, you're going to get the fact that the EMF is 0 at 90 degrees when the coil is 90 degrees to the field, and the EMF is going to be greatest when it's parallel to the field because of the fact that it's constantly rotating. So now let's move on to the alternating currents. Alternating currents are constantly changing. So voltage across a resistance in an alternating current would go up and down in a regular pattern, sometimes increasing, sometimes decreasing. So you can use an oscilloscope to display the voltage of an alternating current. So the vertical height of an oscilloscope at any point in time shows the input voltage at that point. You can choose how many volts per division you want your y-axis using the Y gain control dial. So you can select how many volts per division you want on the y-axis using the Y gain control dial. So the y-axis could represent any amount of volts per division. So one division is say 5 volts or 10 volts or 1 volt. You can change this using the Y gain control dial on the oscilloscope. So an alternating source of alternating current gives a regular repeating sinusoidal waveform. And a direct current causes a voltage that stays the same, so you would see a horizontal line or a dot on your oscilloscope. I'll explain why you would see either a horizontal line or a dot. So on an oscilloscope, you could have your x-axis as time. And let's say we have an alternating source, so your trace would look something like this. As you can see, it's alternating and repeating. So you'll have a regular repeating sinusoidal wave like this. However, if you have a direct current, so if you get a direct current, it will look something like this, where it's constantly at the same voltage across the time. So this is for AC, which is alternating current, and this is for DC, direct current. And this is when the time base is on. And when you turn the time base off, it literally means that your y-axis or your x-axis is no longer taken into account into the oscilloscope. So instead of a waveform or a direct line, it will just compress onto something only on the vertical axis. So for the AC example, you would just have a line that goes from the maximum all the way to the minimum, like that. And this would be on the oscilloscope. And for DC, instead of a line that goes across, you would just have a singular point on the line, like that. And these are the different traces you can see on oscilloscope. So now let's move on to the root mean square and the peak-to-peak voltages. An alternating current, if you have a trace that looks something like this would be your time period of your oscillation of the alternating current. So this is your time period, and this would be the peak voltage. So therefore, this would be your peak-to-peak voltage. And you can find your time period and your peak-to-peak voltage using an oscilloscope. So because your trace will look something like this in your oscilloscope, you can find your time period by finding the number of times per division between the two, and using your times per division, the time per division multiplied by the number of divisions, you'll find your time period. And then again, from peak to peak, you would just do your volts per division, multiply the number of divisions between each peak and peak. And it might help to use the time base off to calculate that. So you can just measure from here to here. And for your time period, you could just measure how many divisions are from here to here, and then multiply it by the time per division. So the power output that you can calculate using the peak voltage is not the true power output of the source, because remember, power is equal to IV. If you use IV peak, this is not equal to true power. So to find the true power, instead of using the peak voltage, you could use the RMS voltage instead, which is the root mean square voltage. And to find the root mean squared voltage, you would just use your peak voltage and divide it by the square root of 2. And if you have a peak current, instead you would use IRMS is equal to the peak current divided by root 2 as well. So to use you always use your root mean squared to find your actual average power from an alternating current. So to find your average power output from an alternating current, so remember, because when you have the higher voltage, you'll have a higher power, and when you have lower voltage, you'll have lower power. So to find the average power over time, because your power constantly is changing, to find your average power, you would just do your current root mean squared, current multiplied by your voltage, also root mean squared. So your root mean squared voltage multiplied by your root mean squared current. Using the trace, remember, you can find your time period. You can use this to find your frequency, because 1 over time is equal to your frequency of the oscillation of the alternating current. For example, in the UK mains, it says that it is at 230 volts, but this is actually the root mean squared voltage of the mains that you get out of your plugs in the UK. So now let's move on to transformers. Transformers work by electromagnetic induction. And what they do is they change the size of the voltage for the alternating current using EM induction. So they change the size of the voltage. This is because you have alternating current flowing through the primary coil, through a primary coil of the transformer, and it produces a magnetic flux. And this causes a change in magnetic field as there is alternating current, so you'll have a changing magnetic field because of the change. There's either a lot of current or little current, and it keeps oscillating. And this is passed through an iron core and to the secondary or output coil. And because you have a change in magnetic field, you will induce a voltage of the same frequency as the input voltage in the secondary output coil. So these are all the steps of how a transformer works. So you have AC in the primary coil, and it causes a magnetic flux, produces a magnetic flux in the coil, which causes a changing magnetic field because it's AC, and because it goes through an iron core, the secondary output coil feels that changing magnetic field, so a voltage is induced as the same frequency as the initial primary coil. Now, using Faraday's law, you can actually calculate the EMF induced in the coils. Remember, Faraday's law was the equation of the voltage, or the EMF induced is the change in flux linkage over time. So if we apply this to the primary and the secondary coils, you'll get primary coils like this and a secondary coil like this. Now, if you rearrange the equation to get your change in flux over time to the subject, you'll get, and assuming the transformer is 100% efficient, you would have the same rate of change of magnetic flux over time for both coils. So you can equate these two equations and cancel out this one. So you'll get, and if you rearrange this, you'll get, and you can just memorize this equation as it's very simple. It's just a fraction where you have the number of coils at the top and the voltage at the top. So for the secondary coil, you have number of coils in the secondary, number of coils in the secondary coil at the top with the voltage of the secondary coil at the top, and a number of coils in the primary coil at the bottom, and the voltage of the primary coil at the bottom. So you have the number of coils of secondary at the top, voltage of secondary at the top, and the number of primary at the bottom, and voltage of primary at the bottom, and the voltage is on the same side, and the number of coils on the same side as well. So it's really easy to remember. So you have two different types of transformers. One is called a step-up transformer, and one is called a step-down transformer. And in a step-up transformer, you would increase the voltage from the primary to the secondary, and there are more turns on the secondary coil. And in a step-down transformer, you have basically the opposite. The step-down transformer decreases the voltage, and there are fewer turns in the secondary coil. So step-up always increases, and step-down decreases. So now let's draw how a transformer actually looks like, because we haven't seen how it looks like yet. So a transformer looks something like this. So now let's label this diagram. So this is a step-up transformer. So the primary coil would be the one on the left with some less coils, or less turns in the coil. So the other coil with the more turns in the coil would be the secondary coil. And in the middle, so this whole thing over here, would be the iron core. And as you can see, it is laminated. I will explain why in a moment. So if the iron core wasn't laminated, you would have eddy currents being produced in the iron core, which generate heat, and this dissipates energy. And the eddy currents are induced by a changing magnetic flux inside of the core. And this creates a magnetic field against the field that's induced, reducing its field strength. So they're induced by the magnetic field, changing magnetic field by the AC current, and it creates another magnetic field which opposes the magnetic field that induced it, and in the end it reduces the total field strength of the magnetic field that is induced by the primary coil. Now let's look at a core which is laminated. So to laminate it, you would have insulation between the different iron cores, which reduces the eddy currents. So let's see how it does this. So say you have a core which has no lamination, and you have the coil going around the outside here. The eddy current will look something like this, where you have charges moving in a circle like this. Now let's see what happens when we laminate it. So as you can see, the charge gets stuck, so there is no current. So laminating the transformer causes there to be less eddy currents, which causes there to be less opposing magnetic fields. So therefore there's a larger magnetic field induced by the primary coil, so that the secondary coil can receive more induction, so therefore the whole transformer would become more efficient by laminating it. And when you laminate them, you put insulation layers in between. So these are insulation layers between the iron core. So now let's move on to the efficiency of transformers. The power equation of P is equal to IV. We can look at the power of two parts of the transformer. So you would have the power on the primary coil and the power on the secondary coil. So let's make two equations again. So instead of P equals IV, let's do it for primary coil, and the power for the secondary coil is just the same for the secondary. And assuming the transformer is 100% efficient, we can just equate these two, and we're going to get an equation of primary for P and S for secondary, and I and V for current and voltage. And we can rearrange this to get. So we talked about eddy currents being formed, which reduce the resistance. Another way which reduce the efficiency of transformers. Another way efficiency is reduced is through the resistance in the coils themselves. Because you have a really long coil of wire, you can expect a lot of resistance. So heat is generated in the resistance of the coils, which causes a reduction in efficiency. So to reduce this, normally a thick copper wire is used for the coils. And because the efficiency is power out over power in, we can write our efficiency as the power of the secondary coil, which is the current multiplied by the voltage, divided by the current times the voltage of the primary coil. So this is the equation for the efficiency of a transformer. So transformers are very important for the national grid, because electricity has to be transmitted at low current to reduce power losses throughout the country. And because the higher the current, the larger the power. You would rather have a lower current to transfer energy, because P is related to I squared of R. So the larger the current, the larger the losses, power losses. So if your current is very high, to keep the same power, you would need very high voltages if you have a low current. And this is to maintain power. Because if you have power with a large current, with a average voltage, it's the same as having a small current and a really large voltage. So the power stays the same and you can reduce the current. So you'll have to go for very high voltages to reduce your power output. So your efficiency of the grid to reduce power losses. So transformers are used to up the voltages for transportation and to decrease them for uses in homes. So say you start off in the generation of electricity, so say a power plant, and you start off with a power from the turbines being created at 25 kilovolts. So you need a step-up transformer to step it up to 400 kilovolts. So you have a very low current, so you have barely any power losses. And when you transport it to homes, you need another step-down transformer to bring it back down to 330 volts, so it's safe to use at home. So this is how you would use transformers in everyday life and the national grid. And this is the end of the video. Thanks for watching. I hope this was useful for you.